Subsurface core drilling confirmed the granite bedrock possessed massive compressive strength, capable of bearing millions of tons of structural gravity loading. Laboratory testing verified exceptional shear resistance, ensuring the bedrock interface would remain impervious under extreme hydrostatic thrust. In 1997, engineers completed the river closure, placing thousands of tons of heavy rockfill to divert the Yangtze into a bypass channel. Excavation crews removed over 100 million cubic meters of overburden, stripping weathered layers to reach pristine bedrock 80 meters below.
A deep grout curtain was injected 100 meters into the rock strata, forming an impermeable subterranean cutoff barrier beneath the dam footprint.
A temporary roller-compacted concrete cofferdam, rising 140 meters, held back the Yangtze while deep foundation excavations advanced. Continuous high-capacity pumping operations evacuated the riverbed pit, exposing the canyon floor for primary foundation treatment. Transverse shear keyways were carved directly into the bedrock floor to provide mechanical interlocking resistance against sliding under hydrostatic head. Cold extruded steel mechanical couplers joined heavy rebar segments, maintaining continuous tensile strength throughout the concrete matrix. Aggregates were refrigerated and combined with shaved ice during mixing, maintaining fresh concrete output temperatures at a strict 7 degrees Celsius. Internal thermocouples tracked thermal gradients in real time, enabling precise regulation of cooling water flow rates to prevent thermal stress fractures. High-capacity cableway cranes spanning the gorge delivered concrete continuously, establishing global placement benchmarks of over multi-layered copper and synthetic rubber water stops were cast across every monolith interface, establishing a dual barrier seal against reservoir water infiltration.
A specialized low-heat Portland cement blend incorporating fly ash and blast furnace slag was formulated to reduce peak adiabatic temperature rise.
Liquid nitrogen injection chilled dry cement stock inside storage silos, suppressing thermal spikes before aggregate batching commenced. Quarried granite was crushed, washed, and sorted into calibrated size gradations to optimize packing density within the structural concrete matrix. Industrial refrigeration plants produce thousands of tons of shaved ice daily, directly replacing mix water to absorb latent heat during cement hydration. Thermal insulated enclosed conveyor galleries shielded pre-cooled concrete from solar radiation during transport across the wide canyon expanse.
Automated fogging nozzles maintain 90% relative humidity over newly cast surfaces, preventing plastic shrinkage microfissures from rapid moisture evaporation.
Closed-loop cooling circuits pumped thousands of liters of chilled water through embedded pipe networks, dissipating internal hydration heat within 14 days of placement. Self-climbing hydraulic formwork systems advanced the monoliths in uniform 3-meter lifts, maintaining precise structural geometry without external ground scaffolding. Compression testing on core samples verified that 28-day structural strength exceeded design specifications by more than 30%. Laser alignment systems monitored contraction joint verticality throughout the 185-meter rise, ensuring plumb monolith interfaces. Verification core samples confirmed that chemical grout fully penetrated the contraction gaps, locking adjacent blocks into a continuous gravity wall. An impermeable high-density polymer coating was applied to the upstream concrete face, providing secondary resistance against chemical leaching and water penetration. As the monolith blocks reached their final crest elevation of 185 meters, construction transitioned to the installation of hydraulic discharge systems.
To manage extreme seasonal floods, engineers constructed 23 surface spillway bays across the central monolith section.
Specialized aeration ramps introduce atmospheric air into the bottom boundary layer of the discharge flow, cushioning the concrete surface against cavitation erosion. Curved ski jump flip buckets direct discharging water jets upward in high ballistic trajectories, dissipating kinetic energy far downstream in the river plunge pool.
Concrete baffle blocks anchored to the riverbed dissipate residual kinetic velocity, forcing turbulent hydraulic jump. High-pressure hydraulic hoists operate the intermediate sluice gates, enabling controlled discharge adjustments under full hydrostatic head. High-strength silica fume concrete was cast along the sediment conduit inverts, resisting abrasion from coarse sand.
With a total discharge capacity exceeding 100,000 cubic meters per second, the spillway structure provides complete flood regulation across the Yangtze Basin.
By configuring discharge schedules across alternate bays, engineers created colliding trajectory paths that force opposing pressure sensors embedded along the flip bucket curvature measure hydrodynamic thrust forces, verifying that dynamic impact loads remain within structural safety margins. A massive reinforced dividing wall isolates the powerhouse discharge channel from spillway turbulence, preventing backwash fluctuations.
Forged steel trunnion pins, each weighing over 20 tons, transfer the entire hydrostatic water load of the closed gates. Dedicated aeration tunnels feed thousands of them.
Scaled hydraulic flume models and fluid dynamics simulations validated every curve of the spillway crest. Precision composite seals on the sluice gate edges withstand high sliding friction against guide slots, providing watertight isolation under intense hydrostatic pressure.
With the hydraulic spillway and energy dissipation architecture verified, focus turned to the underground powerhouse caverns.
Excavated deep within the solid granite mountain ridges, the subterranean powerhouse caverns house 32 giant Francis generating units.
Each 400-ton turbine runner was cast from specialized martensitic stainless steel, engineered to convert Spiral scroll case directs pressurized water evenly around the entire circumference of the turbine, maintaining uniform velocity into the distributor guide vanes. 24 articulated wicket gates pivot simultaneously to regulate water inflow, allowing automated digital governors. Connecting the turbine runner to the electrical generator above, the solid alloy steel shaft transfers Hydrodynamic thrust bearings support the 5,000-ton combined weight of the spinning rotor and water thrust, floating the assembly on a pressurized oil film. Automated filtration loops continuously de-aerate and purify bearing lubricants, ensuring zero particulate contamination. Below the runner, the elbow-shaped draft tube decelerates discharge flows, recovering dynamic pressure head to maximize overall plant energy conversion efficiency. High-frequency pressure transducers monitor vortex rope oscillations inside the draft tube, triggering automated aeration. Protective relay networks monitor neutral ground currents, detecting phase-to-ground microfaults in milliseconds to safeguard the 700-megawatt generator stators. Brushless excitation systems deliver thousands of amperes of direct current to the spinning rotor field poles, stabilizing generator terminal voltage during sudden grid fluctuations. High-strength steel penstocks, spanning 12 meters in diameter, deliver 950 cubic meters of water per second to each turbine under full load.
Ultrasonic acoustic flow meters calculate real-time penstock discharge volumes with 0.1% accuracy.
Subterranean single-phase transformers step up generator terminal voltage from 24 kilovolts to 5.
Advanced synthetic ester dielectric fluids circulating through automated cooling radiator banks dissipate internal thermal loads, maintaining kits.
Sulfur hexafluoride gas-insulated switchgear houses all 500 kilovolt circuit breakers inside grounded metal enclosures. Microprocessor-monitored sensors track internal insulation pressures in real time, detecting fluctuations long before system integrity can degrade. Positioned high on the mountain ridge above the dam, the outdoor switchyard coordinates power routing across national grid interconnects.
Balancings. Giant solid-state converter stations convert alternating current into 800 kilovolt direct current.
Heavy direct current smoothing reactors filter out harmonic current ripples, ensuring stable, ripple-free direct current enters the long-distance transmission corridors. Ultra-high voltage transmission lines span mountain ranges and river valleys, delivering clean hydroelectric power directly to major
To maintain commercial shipping past the 113-meter dam drop, engineers carved a dual-flight, 5-stage navigation. Deep vertical excavations, reaching 170 meters into the mountain, were stabilized using over thousands.
Floating mooring bits glide smoothly along vertical wall tracks, keeping vessel mooring lines balanced and secure. Standing as tall as a 14-story building, these mitra gates represent the largest navigation lock barriers in the world. Sealing precision rubber seal assemblies mounted on the gate vertical contact edges compress under hydraulic pressure, guaranteeing zero leakage between adjacent lock tiers. Reverse sector culvert valves regulate multi-thousand-ton water flows into the chambers, operating without cavitation damage under full reservoir pressure. Continuous subsurface drainage arrays line the rock walls behind the lock chambers, neutralizing hydrostatic groundwater pressure against the concrete liners. Aeration grooves draw high-velocity atmospheric air into the boundary layer, preventing destructive hydrodynamic cavitation from tearing concrete surfaces. Over 12,000 automated geotechnical sensors embedded inside the dam continuously monitor concrete displacement. Inverted plumb lines anchored 70 meters deep into bedrock detect micromillimeter tilting of the gravity monoliths against reservoir hydrostatic loading.
Bedrock drainage curtains relieve subsurface hydrostatic uplift pressure beneath the dam footprint, ensuring monolithic stability against sliding forces.
Housing 32 main hydro generator units across 2 powerhouse complexes, the installation delivers The 700-ton vertical rotating assembly spins at precisely 75 revolutions per minute, supported by pressurized hydraulic thrust bearings. Step-up transformers convert 24 kilovolt generator output directly to 500 kilovolts for long-distance ultra-high voltage transmission. Ultra-high voltage direct current transmission lines export power across thousands of kilometers, supplying industrial load centers in Shanghai and Guangdong.
The twin-track 5-stage lock flight enables 10,000-ton barge fleets to climb the 113-meter elevation difference in 4 hours.
Dual hydraulic rams exert thousands of kilonewtons of force to pivot the 40-meter-tall miter gates against water resistance without dynamic vibration. Heavy elastomeric fenders protect the chamber concrete from hull contact, as turbulent filling culverts raise chamber water levels at 2 meters per minute. For passenger vessels, the vertical gear-driven ship lift functions as a massive elevator, hoisting 3,000-ton ships inside a water-filled chamber. Dedicated mechanical maintenance vessels patrol the intake perimeter daily, clearing floating debris to safeguard underwater trash racks and penstock openings. Overhead gantry cranes can deploy 50-ton steel emergency intake gates within minutes, isolating any penstock line for dry tunnel maintenance. Deep underground transportation tunnels provide heavy component rail access directly between surface fabrication yards and subterranean turbine galleries.
Navigability along the upper Yangtze was transformed from a perilous canyon passage into a modern deep-water shipping artery.
Continuous automated optical collimation systems track dam crest horizontal alignment across the entire 2-kilometer crest length, down to fractions of a millimeter. Dewatered draft tube inspections reveal how hydraulic profiles maintain smooth laminar discharge flows, minimizing back pressure against rotating turbine blades. Automated motorized trash rakes clear submerged intake screens against 40 meters of hydrostatic depth, preventing turbine inflow blockage. Babbitt metal thrust pads sustain vertical downward thrust forces exceeding 5,000 tons, floating the massive rotor assembly on a thin hydraulic oil wedge. Robust concrete training walls guide turbulent high-velocity discharge currents safely downstream, preventing localized bank erosion along the natural riverbed. High-capacity deep sump pumps automatically evacuate continuous foundation seepage, preventing water buildup across subterranean inspection networks. Pre-stressed anchor tendons drilled over 60 meters deep into fractured karst formations permanently stabilize sheer rock abutments above the powerhouse vaults. Massive bottom pintle bearings carry the dead weight of each 800-ton steel gate leaf, rotating smoothly over decades of submerged maritime service. Miles of fire-resistant control cables and fiber-optic data channels interconnect subsurface power plants with the central dispatch network. Overhead crest gantry cranes travel along embedded tracks spanning the entire structure, capable of deploying intake bulkheads and maintenance gear at any monolith. Vibration sensors continuously record micro-vibrations across turbine shafts, automatically alerting operators to mechanical imbalance before bearing wear can develop. Outdoor switchyards route generated electrical power into multiple high-voltage transmission lines, feeding eastern and southern power grids across China. Engineered approach canals buffer river currents, providing calm water zones where commercial convoys align safely before entering the lock chambers. High-pressure electrohydraulic governors regulate turbine wicket gate opening angles within milliseconds, maintaining steady grid frequency during sudden load rejections. Non-contact optical temperature monitors scan high-current busbar connections 24 hours a day, preventing thermal hotspots across electrical conductors.
Deep borehole optical logging systems inspect the internal granite matrix beneath the grout curtain, confirming no subterranean voids develop under water pressure.
High-sensitivity triaxial correlate to the dam base record regional tectonic vibrations.
Sacrificial galvanic anodes and cathodic protection systems shield submerged turbine components against galvanic corrosion and mineral pitting. Reverse tainter culvert valves open smoothly beneath high hydraulic head, allowing lock chambers to fill by gravity without dangerous turbulence or cavitation. Continuous acoustic Doppler telemetry maps sediment transport dynamics along the upper reservoir floor, guiding seasonal bottom outlet scouring operations. Advanced composite wraps reinforce subsurface powerhouse support columns against cyclic mechanical vibrations generated by continuous high-load turbine operation.
Gas-insulated bus lines route thousands of megawatts up vertical cliffs to medical gorge cliffs to surface with zero environmental footprint.
Closed-loop environmental filtration systems treat all powerhouse drainage water, capturing oil residuals before any liquid is returned to the river. Mechanical shear pins on wicket gate linkages provide fail-safe overload protection, shearing instantly if foreign debris jams an individual guide vane. Precision hydraulic docking seals lock the ship lift chamber watertight against the approach canal, allowing ships to enter without water loss. Automated optical turbidity sensors continuously test foundation seepage water, verifying that subsurface grout curtains prevent fine particle migration from bedrock.
High-volume underground ventilation shafts circulate fresh air throughout deep cavern complexes, maintaining stable.
Heavy structural steel stop logs stored along the dam crest can be lowered into spillway slots to permit dry dock maintenance of radial gates. High-pressure nitrogen-charged accumulators store emergency hydraulic energy, guaranteeing full gate closure even during complete station blackout events. Operating in seamless balance with nature, the megastructure secures energy resilience and navigation reliability. Distributed fiber optic sensing cables embedded within concrete lift joints detect micro-strain variations across the dam core in real time. Closed-loop demineralized water circuits circulate directly through hollow stator copper bars, dissipating electrical heat without conductive current leakage. Heavy spherical bearings absorb multi-directional structural deflections during spillway discharge operations, preventing mechanical binding on cylinder shafts.
Microprocessor-based numerical relays provide dual redundant protection across generator lines.
Bottom distributed filling culvert ports disperse inflow water evenly across the chamber floor, preventing localized vortices that could destabilize moored ships. Subsurface vibrating wire piezometers measure hydrostatic pore pressures within foundation rock pores, verifying that grout curtains block seepage pathways. Tail race portal cranes handle draft tube maintenance gates, allowing individual hydro turbine discharge tunnels to be dewatered for annual blade overhauls. Heavy structural steel stop logs stored along the dam crest can be lowered into spillway slots to permit dry dock maintenance of radial gates. Thousands of tons of counterweights balance the water-filled ship lift basin, reducing electric hoisting motor power requirements to minimal levels.
Infrared thermal scanning arrays continuously monitor transformer bushing connections, detecting contact resistance variations before localized overheating can develop.
The massive spiral scroll case directs pressurized inflow water evenly into the turbine runner perimeter, maximizing.
Grounding brush assemblies safely discharge electrostatic currents from the rotating shaft to ground, preventing electrical pitting damage across precision bearing surfaces. Dedicated seismic stations anchored directly into the foundation granite register regional tectonic tremors, confirming the dam's specialized bottom rubber seals compress tightly against machined stainless steel sill plates, maintaining a watertight barrier across 20 meters of hydrostatic head. Continuous chromatographic gas analyzers test transformer dielectric oil daily, detecting minute trace gases that signal insulation degradation. Precision V-notch weirs record seepage discharge rates across every monolith, confirming that bedrock drainage holes remain open and functional. Heavy helical synchronization shafts link all 4 hoist corners mechanically, ensuring the water-filled lift chamber remains level within fractions of a millimeter. High-response electro-hydraulic proportional valves adjust water flow through wicket gates within milliseconds, providing grid frequency stability during load changes. From raw granite excavation to monumental civil operation, the Three Gorges Dam represents human ingenuity. Capacitive displacement joint meters measure micromillimeter breathing between adjacent monolith blocks, confirming thermal expansion remains within safe structural limits. Heavy generator bus bars are braced with rigid epoxy glass supports to withstand electromagnetic repelling forces during severe short-circuit events. Auxiliary lubricating oil pumps undergo rigorous shaft alignment checks, ensuring continuous pressurized oil flow to heavy generator guide bearings. Massive steel trash rack structures anchor into reinforced concrete guide slots, blocking submerged floating timbers from reaching high-velocity turbine penstocks. Continuous laser particle counters monitor hydraulic governor fluid purity, preventing microscopic contaminants from causing valve spool stiction. High-pressure grout curtain inspection heads allow engineers to measure residual uplift permeability across deep granite foundation fissures. Replaceable bronze alloy wear plates protect structural steel gate leaf edges from frictional abrasion during repeated lock opening cycles. Compact gas-insulated switchgear installations provide reliable high-voltage switching in steep mountain terrain with minimal footprint and maximum safety. High-resolution optical encoders detect shaft rotational speed variations down to hundredths of a hertz, feeding real-time telemetry to
bolted pressure manholes provide sealed access into dewatered penstocks for non-destructive magnetic particle weld testing during major overhaul cycles.
Automated crest meteorological stations record local wind loads, ambient temperatures, and barometric trends.
Continuous excitation system vibration monitoring ensures brushless exciters deliver stable direct current to rotor field poles without mechanical resonance. Subsurface relief boreholes relieve uplift pressure beneath the powerhouse foundation slab, channeling natural seepage safely to automated drainage sumps.
500 kilovolt transmission substations coordinate power distribution across long-distance direct current corridors.
Massive converter valve halls transform alternating current into direct current at 800 kilovolts, minimizing power transmission losses across thousands of kilometers. Giant smoothing reactors filter out harmonic ripples from direct current power lines, guaranteeing grid stability before energy enters long-distance transmission corridors. Continuous geological core drilling confirms the underlying granitic bedrock remains completely unweathered and impervious beneath decades of massive hydrostatic loading. Solar-powered hydrological monitoring buoys collect real-time water temperature, sediment density, and water quality data. Dedicated heavy diesel backup generators guarantee uninterrupted emergency electrical power to station drainage pumps and spillway hoist controls during regional blackouts.
Deep drainage centrifuge separators treat all collected seepage water, removing mineral particulates before discharge into the downstream river channel. Digital gas density monitors track dielectric insulation pressure inside high-voltage switchgear, preventing electrical arcing across high-voltage circuit breakers.
Paired 1,200-ton bridge cranes work synchronously to lift and seat hydrogenerator rotors weighing over 2,000.
Non-destructive ultrastick thickness testing verifies that heavy alloy steel penstock liners suffer zero wall thinning after independent mechanical wedge arresters provide fail-safe emergency braking, locking the entire ship lift chamber instantly if hydraulic pressure drops unexpectedly. Subsurface energy dissipator blocks break up high-velocity culvert water jets during lock chamber emptying cycles, preventing scour damage to concrete conduits.
High-capacity axial ventilation systems continuously purge subterranean turbine caverns with fresh mountain air.
Automated piezometer networks measure pore pressure gradients throughout the foundation bedrock, alerting operators to any changes in subsurface drainage efficiency. Upstream floating retention booms intercept driftwood and floating river vegetation, ensuring submerged intake trash racks remain clear during high water seasons. Bedrock pressure monitoring manifolds verify that foundation grout curtains successfully eliminate high-pressure water seepage beneath the powerhouse floor. Cathodic zinc anodes mounted on submerged hydraulic components provide passive galvanic protection, shielding high-strength alloy steels from electrochemical corrosion. High-capacity intake gantry cranes deploy emergency bulkhead gates within minutes, enabling complete dewatering of individual penstock lines.
The dam is critical. I'm seeing pressure anomalies on the main structure. Initiate emergency reroutes. Loads are spiking. We're losing capacity.
Ultra-high voltage direct current transmission corridors span across rugged mountain terrain, delivering over 100 billion kilowatt-hours of clean electricity annually.
By taming the turbulent rapids of the Yangtze River, the mega project created a vital deep-water shipping channel.
Thousands of embedded fiber optic sensors monitor internal strain and micro-deflections continuously, guaranteeing structural health.